Okay, so today we're going to start chapter 4, which is our look at probability theory. As I mentioned in our last session, this is really the foundation of all of statistics right here. Probability theory is a very interesting branch of mathematics, and everything we see here is going to translate into statistics in some way. Now, unlike the other chapters, this one is a little bit more theoretical. So that means you won't expect to see a whole lot of Excel in here, but there's a lot of important information. So we'll start with the idea that what is probability theory all about? It's really just a way of quantifying uncertainty. Okay, so in other words, there's a lot of situations in business applications with uncertainty. And of course, it would be ideal if we could come up with a way to at least quantify it. So in other words, probability theory is designed to quantify uncertain events that may take place in the future. Just a classic example of this would be the weather. I mean, if you go look at any weather forecast, I'm going to look at one right now. What you're going to see is not just the weather, the temperature, that kind of thing, but they often will try to give you some idea of what is the likelihood of precipitation, let's say. So, you go look and you'll see that it's calling for, let's say, a 30% chance of rainy weather tomorrow. So right now, this one says tomorrow. Yeah, look at those probabilities. Yeah, according to what I'm seeing here, there's a roughly 20% chance it'll rain in the morning, and that continues to increase until it gets into the 50s in the afternoon, and then it sort of tapers off. So where did these numbers come from? Well, that's a very good question. Now, every discipline is a little bit different in how it uses probability, but ultimately, the statement that tomorrow there is a 50% chance of rain is a probability. It's called a probabilistic statement, which means that we don't know for a fact that it's going to rain or not rain. What we do know is based on our best scientific evidence and past experience, we're going to make a claim here that there's a 50% chance of rain, which means, of course, there's a 50% chance of no rain, and that will help us plan for tomorrow. Now, we see a lot of probability theory used in like finance, for example. Especially if you have a lot of investments, probability theory can be used to estimate the likelihood that a stock will increase in the future, for example. Now, of course, it's very difficult to do this properly, but at least given all the information you have about a corporation's earnings and their expenditures on research and development and, the new products they're developing, you want to have some way of deciding, what percent is the likelihood that next year the stock price will go up, let's say 10%. So there's a lot of potential applications for probability theory. But again, the ultimate goal of it is to assign numbers to uncertain outcomes in the future, as opposed to just purely guessing. Okay. I mean, clearly we know that it might rain tomorrow, but that's true of every day. But some days it's more likely to rain than others because of the pattern of, let's say, the humidity or the wind speed or whatever the case may be. So we'd ideally like to have some numbers to look at to help us make informed decisions. All right. So anyway, how does this work? By the way, here's some of their examples. These are also probabilistic questions. What are the chances that sales will decrease if we increase prices? Well, again, in economics, we'd like to have a model that would help us understand, the price elasticity of demand for a product, and that in turn could help us decide if I raise my prices 10%, what's the likely outcome on the demand for my product? Or if I'm a manufacturer and I produce some new product, what's the likelihood that it increases productivity? Or in the area of finance, we'd like to know the odds that some new investment, some stock that I bought, for example, will make money next year. So probability is a number that represents the likelihood that an event will occur. So the way that they're set up is that probabilities are either defined on a scale from 0 to 1, or else they're represented as percentages, which means they would go from 0% to 100%. Okay, so in other words, for example, a probability of 0.5 is equivalent to a probability of 50%. It means the same thing. Okay, so if I told you that there's the probability of it raining tomorrow is 0.5, it means the same thing as saying there's a 50% chance that it will rain. Now, low probabilities mean something is unlikely to occur. 0 means it's impossible. So a probability of 0 means that an event is impossible. Like, for example, the probability that the sun will rise in the west tomorrow is 0. It's not going to happen. Okay. It's not unlikely, it's impossible. A probability of 1 at the other extreme means that an event is guaranteed to happen or certain. So we could say the probability that the sun will rise in the east tomorrow is 1 or 100%. It means the same thing. And then everything else comes somewhere in between. Like for this example with the rain, we don't know for a fact that it's going to happen or not happen. So that's why that probability is somewhere in the middle. Okay, it could be 10%, it could be 20, 50, 90, but it can't go outside that range from 0 to 1. 50% means it's equally likely to occur or not occur. And so now here they're talking about the idea of experiments. Experiments do take place in scientific disciplines like biology and chemistry and physics, where you manipulate the results or you try to see what's going to happen. If, for example, you mix two chemicals together, you may want to know if it results in some new substance or other, or if the result is something that can be marketable or whatever the case may be. In business, though, we don't really run experiments as such most of the time. It's not impossible, but it's not as common as you would get in the sciences. So, but sometimes sometimes we can do an actual experiment. And if we do, we refer to them as random experiments. So a random experiment is a process in which an action is repeated each times, and the results are observed. For example, something as simple as this: the process of rolling a pair of dice could be counted as an experiment. Now, in a case like this, we know in advance, because we know how the dice are structured, we know in advance the probabilities of the different possible outcomes, which means anything from 2 to 12. But we don't know what actually will happen. So we call this a random experiment because of the fact that the outcome is random or unknown in advance. Okay, so this is what we mean by a random process or random experiment. Um, Now, of course, like I was saying, in other disciplines, we might see different kinds of experiments. You might, for example, like I was saying in a chemistry class, you might go out of your way to combine a chemical with other chemicals to see what happens. But here, some process is generating random outcomes or random results. And what we're trying to do is observe them and see the likelihood of this particular outcome occurring. So, for example, with the dice, I can determine in advance the likelihood, let's say, of getting a seven. But of course, I'll never know if it's actually going to happen until I actually roll the dice. I do know it's most likely. So if I'm playing a game like craps in a casino, I know upfront what numbers are likely to turn up, and I can place my bets accordingly. But of course, I can't see into the future, so I'll never know until the dice are actually rolled what the actual outcome will be. Okay, now an experiment simply means that we're repeating a process over and over again and generating outcomes. Okay, so the process of rolling the dice multiple times is defined as an experiment. Each roll is defined as a trial of the experiment. Okay. So, like I might be rolling the die 5 times or 10 times or 20 times, and I would like to know in advance or try to determine the likelihood. Let's say I roll the dice 5 times, and I want to know the probability of all 5 of them being a seven. I can do that based on my understanding of how the dice are set up. In other words, I know what the numbers are and how likely they are to turn up. Now, the sample space of an experiment, and this is a huge important definition, by the way. The sample space of an experiment is a set containing all the possible outcomes of the experiment. And it's always expressed as a set, and it's designated with the letter S. So in our dice rolling experiment, it would look like this. Right? I don't have to write them all. So if you remember, this notation, these are braces, and these are used to represent a set, and a set is simply a collection of objects. Right? Often it's numbers, but not always. You would have been exposed at some point in your mathematical careers to set theory. Okay, there are algebraic operations we can perform on sets, and we'll discuss that later on. But right now, it's enough to recall the idea of a set is simply a collection of elements. And of course, a set can be finite or infinite. Here, we're going to restrict ourselves to finite sets. So, for example, the set of all Major League Baseball teams, let's say, is a finite set because it only has 30 teams. Set of all, let's say, integers is infinite because there's an infinite number of integers. So, oh, and by the way, when one possible outcome of an experiment is referred to as a sample point. Okay, sample point because it's a single possible value taken from a sample space. So, like in my example, the dice, each of those outcomes, 2 through 12, is a sample point. So here's some more examples of experiments you might run across tossing a coin. In that case, the sample space consists of heads and tails. Inspecting a part, in that case, the sample space consists of defective and non-defective. Conducting a sales call, you can see that the sample space is either somebody bought your product or they didn't. Rolling a single die, you can come up with a number from 1 to 6. And then finally, two teams play a football game, and either they win, they lose. One team either wins, loses, or ties the game. And again, you notice some of these are numbers and some are not. Most of the time, we'll be dealing with numbers. Now, this one is a little bit different because you've got a company that's building a power plant of some kind, and there's two stages. We design and we construct. And the design stage and the construction stage each have different probabilities for the amount of time that they will take. So there's this little diagram. Let me just show it to you real closely. Is supposed to represent all the possible outcomes of this experiment, which essentially consists of observing how long it takes for this project to be completed. So if you notice the step 1 design, there's only three possible values, 2, 3, and 4 months. And then once we have that part completed, the construction part will either take 2, 6, 7, or 8 months. So that leaves all these different possibilities. If we go up this first branch, that means it took 2 months to design the power plant and 6 months to construct it, which means a total of 8. If instead, after a 2-month design process, it took 7 months to complete this project, that means it took 9 months, okay, et cetera, et cetera. Now, we don't know what the probabilities are of these different possible outcomes. The only thing we do know is that the outcome, which means the total time to completion, is going to be either 8, 9, 10, 11, or 12 months. So for this experiment, cell space is 8, 9, 10, 11, and 12. Now, if we knew the probabilities of these 3 different times for the design and for the construction, we could then calculate the probabilities of each of these outcomes, but we don't have that information at the moment. But if we did, we can certainly easily calculate all of these probabilities. Now, here's an interesting concept. Now, this is getting us into an area called combinatorics, which is basically the mathematics of counting. That's really what it is. This is an area that overlaps with computer science. And so there's different concepts that we need to understand in this area. So we'll start with a simple one, and that's this notion of factorial. So factorial is a mathematical operation, usually written like this. This is pronounced n factorial. And by the way, this is on your calculators. How is it defined? Well, it's a very interesting operator. It looks like this. First 2 values are 1. Okay, we can't have any fractions. We can't have any negatives. Factorial is only defined on the non-negative integers. But once we get past 1, it starts to get very interesting. Now, you may have run into this, by the way, in finite math. In fact, you probably did. All right, but maybe it's been a while. So let's go ahead and review all these concepts. All right, now, because these numbers can get very large very quickly, it might be nice to do this on the TI-84, and that certainly is possible if you know how to do it. So to obtain these results on the TI-84, here's what you have to do. So the first thing you have to do is hit the menu math. Actually, it's the button math, followed by the menu PROB for probability. Um, Actually, I just realized I've goofed here because if we wanted to know, for example, the value of 5 factorial, that has to come first. So let me take a step back here. So what you have to do with this calculator is you have to type the 5 first. All right, so that's where I messed up. So let's do that. Hit 5. And then we can start. 5 math, prob, enter. Oops, what happened? There we go. Now, once you hit prob, you're going to see a very long menu of items in the area of probability theory that we would like to know the answer to. The one you're looking for is number 4. And you'll recognize that exclamation point, that is the symbol for factorial. So if you choose number 4 and hit enter, it'll show 5 factorial on your screen, and then you hit enter again. And we'll come back with the correct answer, which is 120. All right, so it's not that difficult. You just have to get used to the way the calculator is set up. Now, this one is obvious. I mean, sure. I mean, based on what you're seeing here, it's pretty clear that 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. But what if we wanted one of the big ones? Something as simple as even 10 factorial. You start with 10. You might be surprised when you see this. 10 math prob. Okay. Scroll down to number 4. Enter twice. And you're going to get, let's see, what is that number? 3,620,800. Wow. So from 5 to 10, it went from 120 to over 3 million. So it grows very, very quickly. Now, by the way, I do want to mention here that for extremely large numbers, the calculator uses scientific notation. And how would that look? So if you see something like this in the calculator, this means 3.600 times. Actually, let me use a different example so you don't get confused. Let's try a 9 there. That E9 means whatever number you have on the left, you're multiplying it by 10 to the 9th. Okay, so if you try, if you want to see this, we'll try 30 factorial. Oh, I think you'll be in for a bit of a surprise when you see this. 30 math prob. Scroll it down to 4, of course. And enter twice. And then, oh my God, look at that, 2.6525, let's say, E32. Okay, so I just realized on this calculator, it uses a capital E. They're all different. So that means that, although I've, got rid of some of the digits, this is approximately equal to 2.6525 times 10 to the 32nd power. Wow. Anyway, so what is it exactly do we need this for? All right, well, let me show you an example of this. Factorial operator is used to determine the number of ways that n objects can be arranged. Now, what exactly does that mean? All right, well, imagine the following situation. Um, you've got a very big living room, and you've got room on your wall for 3 paintings. All right, let's just call them 1, 2, and 3. Now, here's the thing. How many different ways can you hang these paintings? Well, clearly, this is just one of them. What other possibilities are there? You got 1, 2, 3, 1, 3, 2, 2, 3, 2, 3, 1, 1, sorry, 3, 1, 2, and 3, 2, 1. Each one of these ways in which I've ordered the paintings is referred to as an arrangement. And you notice there are 6 of them. Now, why is that, by the way? If you look at the position of the paintings, these are the rooms for this is where your paintings can hang. For the first painting, you have 3 choices. Once you've chosen that first painting, there's only 2 left. That means there's only 2 ways of choosing the second painting. And then once you've chosen that one, there's only 1 left. And that means for the third spot on your wall, you only have 1 choice. So the number of choices is 6. But guess what? Guess so is 3 factorial. So in other words, no matter how many paintings I have, I can hang my paintings in n factorial different ways. Actually, I should have said my n paintings in n factorial different ways. Okay, so in other words, n factorial shows the number of arrangements that can be created with n objects. Okay, and each way in which I lay them out from left to right is an arrangement. So if, for example, if instead I had room for 4 paintings, there would be 4 factorial, 4 times 3 times 2 times 1, 24 different ways of hanging them, each of which is a different arrangement. Okay, so that's the starting point for what we're going to do with our brief introduction to combinatorics. this notion of the factorial operator and the concept of arrangements. Now, what they're going to do next is introduce the idea of what happens if I don't choose all the objects. So in this next section, if not all the objects are chosen, the formula for determining the number of ways which the objects can be chosen obviously has to be modified. Now, here we've got two possibilities. We can form what are called combinations, where objects are chosen from a group in such a way that the order of selection does not matter. We also then have permutations where the objects are chosen from a group in such a way that the order of selection does matter. Okay, so let's see. Let's come up with some examples here. And then we'll look at some formulas. Suppose that, well, let's think about the paintings example again. Suppose that a homeowner has 10 paintings, but only room for 3. Well, that, I mean, that, of course, paintings take a lot of space. How many ways can a homeowner display his paintings? Now, the number of possibilities now is very different. And so, by the way, because the order in which I hang them does matter. In other words, having Picasso followed by Braque and Leger is just different than having Picasso last, for example. So the order in which I hang them does matter. You can see the difference when you walk in the room. The order in which I hang the paintings makes a great deal of difference. So, but I have 10 paintings, so the number of possibilities is quite large. I could, for example, have 1, 2, 3, 3, 1, 2. And now all of a sudden I can have 4, 1, 7, this kind of thing. And if you notice, even though this represents the same group of paintings, the order changes the appearance in the room. So therefore, each of these is a different permutation. So you can imagine there's going to be a lot of this. We don't want to sit here and write them all down like we did with the arrangements. So there's a formula for this. And we're going to go find it in the slides. And we'll see how that works. Here it is. Let's copy this. So here's the notation that they're using. N is the number of objects selected. N is the number, or the size, let's call it the size of the group. If the objects are selected from. All right, let's do this. Okay, now this can be written in several different ways, as you can see. But in our example here with the paintings, since we have 10 to choose from, but we only have room for 3 of them, that implies that for the painting example, the capital N is 10 and lowercase n is 3. Okay. So according to this formula, the number of permutations or the number of ways we can choose our paintings and hang them on the wall is 10 factorial over 10 minus 3 factorial, or 10 factorial over 7 factorial. Now, there's a couple of options I have here. I can go back to my calculator using the techniques we just learned and calculate 10 factorial, which actually we just did a little while ago, but let's do this again. So this one is a 3,628,800. 7 factorial is 1540, and that ratio is equal to 720. That's a lot. Imagine if we tried to write them all out. So in other words, there's 720 different ways I can choose the 3 paintings and then hang them. Right. So each one of those choices is called a permutation. How do you like that? Now, the calculator can help us with this. All right. So um, so it has a function built into it that will do this for us. Now, I just want to check one thing here. Um, I'm pretty sure. Yeah, this is what I thought. All right, so here's what you do. If you go to the same math menu we had before, this time you're gonna pick prob again. This time you're not gonna pick number 4. You're gonna pick number 2. 2 is labeled NPR. Now they're using different notation. Um, this is what the book is calling capital N, and this is what the book is calling lowercase n. So when you hit this enter button, it'll look like this. All right. And what it's saying to you is this: tell me first how many objects are you choosing from, and then how many objects are you choosing? And it's always the larger number on the left, in case you forget. If you get it backwards, it'll give you an error message. All right. So if you go ahead and try that, let's see what happens. All right. So remember, it's 10 and 3. Enter, and there it is. 720. It has to be because it's the same formula that the calculator is using the same formula that we are. Okay. Now, if you notice here, permutations are the ones where the order does matter in the sense that 1, 2, 3 and 3, 1, 2 are 2 different permutations. But if the order is not relevant for some reason, instead, each of these choices is referred to as a combination. All right. So let's look at an example of this. So the combinations, the order of selection does not matter. All right. So in other words, let's say that, oh, before we even do that, let's go get the formula from the slides. It's not that different. In fact, there's really only the one subtle difference. If you look at them closely side by side, let me just go copy the other one here, and you'll see right away what the difference is. Right here, this is the only difference between the two. Okay. So let's see if we can dream up an example here. Suppose that suppose that in a class of, let's say, 20 students, uh, three of them are chosen to what do we have them do? To sit on the student council. I guess they still have that kind of thing. I don't know, student government. So in other words, three of them will be chosen, let's say at random. Suppose nobody wants to do this, but the teacher chooses three of them to join the student council and represent the class or the department or whatever. So in a case like that, let's say that the students are numbered from 1 to 20. We want to get bogged down in their names. That would be very awkward. So the students are numbered from 1 to 20. The selection of students 1 to 7 is the same as the selection of students 217, let's say. So in other words, the order in which they're called to do this is not of any consequence. It represents the same thing. It's the same three people who are going to go serve on the student council. So each choice here is known as a combination, since the order of selection is irrelevant. Now, up here, that was certainly not the case because it affected the order in which the paintings were hung, and you can tell the difference between 123 and 312. Not so here. So how many choices are possible in this case? Well, all right then. Let's look at the formula, and then let's go to the calculator. So in this case, capital N is 20. 20 students, I'm picking three of them. You notice how in the calculator it has the number of selection choices in the left. It's, every book is slightly different, every calculator is slightly different. As long as we know which is which, the 20 is the number we're choosing from, the 3 is the number that we're choosing. Now, these are some big numbers. Okay, 20 factorial, 17 factorial, they are quite large. So there's going to be a lot of cancellation. Let's see what we get. Oh my God. um, it's a big number. So what you might want to do here is rather than get involved with rounding problems, you could type 20 using the steps that I just showed you, divided by the product of 3 factorial times 17 factorial. That might be more convenient, because otherwise you might end up with some rounding problems. So given all the digits that are floating around there, I've got 1140. Now, of course, this is not necessary because we can go to the calculator's menu and do the following. Now, remember before we started with math prob, but we went to number 2. This time, we're going to start with math prob. And we're going to pick number 3, NCR. So again, the notation is slightly different, but it should be clear this represents combinations. And just like before, we have dialog boxes. We'll enter the 20 here and the 3 here. And then you'll hit enter, and what do you know? It's 1140. Exactly. All right. So those are the 3 most important concepts in the branch of math called combinatorics. So let me just write it down one more time. We have arrangements, a number of ways that a group of n objects can be arranged. Okay. Permutations, a number of arrangements that can be created by choosing objects from a larger collection. Where the order of selection. And then, of course, combinations, a number of arrangements. That can be created by choosing objects from a larger collection. Where the order of selection does not matter. Okay. So you got to make sure you get those straight. Which one, in which cases the order matter, in which case it does not matter. Combinations, no. Permutations, yes. Okay, don't get those backwards. All right, now you're going to see a lot of this show up in the rest of this course and in stats too, especially this one. The combinations will show up in certain formulas that we'll see later on. Permutations are not quite as important in statistics. It's combinations that are the one that we'll see the most often. All right. Now, with that being said, now we're getting back to the idea of random experiments and probabilities. So one definition we do need here that I neglected to mention earlier is with the random experiment, sample space is a set containing all possible outcomes of the experiment. It doesn't say anything about probabilities, but it's just all the possible outcomes of the experiment. So in other words, remember when we roll the die twice, sample space consists of all the integers from 2 to 12. Okay, those are the only possibilities. Now, we need to define an extremely important concept right now, and that's called the event. An event is a subset or a smaller portion of the sample space. For example, if a pair of dice are rolled, and doubles turn up is an event. Why? Because this is a set consisting of the integers 2, because you get 2 1s, 4, 6, 8, 10, or 12. Okay. So in other words, out of all of the different possible outcomes of rolling the dice twice, only these constitute doubles. We're going to call that E. All right. E is the event. The doubles turned up. And if you've forgotten what this means, doubles means you get 2 of one number, 2 1s, 2 2s, 2 3s, all the way up to 2 6s. So they add up to either 2, 4, 6, 8, or 10 or 12. And of course, E is a subset, meaning it's a smaller portion of the entire sample space. S, which equals, of course, 2, 3, 4, 5, 6, 7, 8, 10, 11, and 12. All right, so that you're going to see that word event over and over and over again. It's going to come up quite often. Now, at this point in the chapter, we're going to concern ourselves with calculating the probability of the different events. So we would like to be able to compute the probability of a given event. And sometimes it's very straightforward, sometimes it's not. So like here, for example, the probability of E is the sum of the probabilities of getting 2, 4, 6, or 12. It's that simple. The question is, what are those probabilities? What is the probability of a 4, for example, or an 8 or a 10? So in order to get a probability like that, in this example, the probability of getting a specific value equals the number of ways of getting that value divided by the number of possible outcomes of this experiment, which is actually 36, which is equal to 6 squared. Okay, now if you wrote down all the possible ways you can roll a pair of dice, it would be 36. So for the 4, it can be rolled by getting a 1 followed by a 3, a 2 followed by 2, or 3 followed by 1. Okay, so the probability of getting a 4 is 3 out of 36. Okay. The probability, in the case of a 12, it can only be rolled as 6, 6. So the probability of getting a 12 is 1 out of 36. So the one that's most likely to turn up, probability of getting a 7, 6 out of 36, because it can be attained or rolled as 6, 5, 3, 4, 4, 3, 5, 2, 6, 1, which just means there's 6 possibilities out of 36. So an event, all of these are events, by the way, getting a 4, getting a 12, getting doubles, they're all events because they're subsets of the entire sample space. All right, now here they're making the claim. So they're going to designate E for the event I, and they're just basically saying here what we saw earlier is that no matter what the event is, its probability is bounded between 0 and 1. Okay, PEI is the event I, whichever one that happens to be, and its probability is bounded between 0 and 1. And of course, all the probabilities, if I were to write the chart of the probabilities of getting 2, 3, 4, 5, all the way up to 12, they would all have to add up to 1. Right, that well, okay, there it is, right there. They have to add up to 1. Okay, because one of them has to be true. If I roll a pair of dice, it has to be one of those numbers. So the total probability of all those outcomes or events is 1 or 100%. All right, what's coming up next? Now, there's different ways of assigning probability. What we're doing now with this dice experiment is actually based on the second method, the so-called relative frequency method, meaning that we know what could happen from historical experience. Now we're going to focus here. We got a classical method where you got now a single roll of the die would fall into this category because all 6 outcomes are equally likely. Relative frequency means that you're considering the likelihood of something happening based on experimentation or historical data, which is the one we'll probably use most of the time. And then the subjective method, we're not going to use this one. This is the one where you have no other information. Like you look out the window and say, what do I think? Is it going to rain? Well, the sky is kind of dark, so I'd say it's like 50-50 that it will rain tomorrow. I have no other knowledge, no other information. So that's the subjective method. We only use that when we have no other information. All right, so here they're going to start with the classical method. So what happened here? We've got the rolling of the die, a single die, that is, and each point is 1 through 6, has a 1 out of 6 chance of occurring. So I could, for example, determine that the probability of getting a 3 is 1 out of 6. I don't need to experiment because I know how the dice is constructed. Here's another, now this is the relative frequency method. Imagine a hospital knows from experience that on any given day, the number of people waiting in the emergency room follows the following table. We've got nobody 2 out of 20 days in our sample. We have in five days there was just 1 person, 6 days there was 2, 4 days there were 3 people, and then on 3 days there were 4 people. This, by the way, this is a frequency distribution. We've seen these before. And so here, given this historical experience, we can calculate the probability that tomorrow, let's say, there's nobody in the waiting room. That would be 2 out of 20, which is 10%. Okay. So it's very straightforward. As long as this is a true representation of how things work at the hospital, we can get some really useful results out of this. And here you see what they've done is they divided each of these outcomes by the total of 20, and those are my probabilities. Although they're all fractions, clearly, for example, 0.25 means 25%. And of course, the subjective method means we're just guessing, basically. Yeah, we don't. All right. So now we're going to come back and formally define an event. It's a collection of sample points, and the probability of that event occurring is the sum of the individual probabilities as we just saw. Okay, so we should always be able to calculate the probability of an event. All right, so then they're coming back with this example of the PowerPoint company or the power company. So let's see, what do we have to do? Oh, yeah, we got a ways to go here. So, all right, I think this was a good introduction to the topic, but I think we'll have to save the rest of this until next time. All right, so when we come back, we'll go over this example And then now what we're going to basically do here is actually take a bit of a detour and review set theory, because it's entirely possible you forgot what you learned in your previous math classes or in finite math for that matter. So we're going to review them to make sure we're all on the same page, because we're going to need them. All right. There's probability theory is ultimately based on sets. Okay. And that's why this is so important. All right. So, but for now, we'll knock it off. And when we come back, we'll get back into it here. Now, in the next chapter, by the way, we're going to be back to calculating a lot of things. We'll need the calculators all the time. This one, like I said, is a little bit more theoretical, but it's awfully, awfully important. So anyway, so next time we'll dive right back into this. So I'll see you then.